Welcome to the Deep Dive. This
Ah,
is where we take those sources you send us, the ones behind your big questions, and we really boil them down. We aim to give you the key insights, those aha moments, without all the overwhelm.
Yeah, getting straight to the good stuff.
Exactly. So you sent us complexity trends across the universe, a shared metric perspective. And you're after those connections, right? How things link up. Our mission today is, well, it's a big one. We're tracing complexity all the way from the Big Bang right up to AI.
It's quite the journey. And this document gives us a really interesting framework, something called the Shared Metric of Complexity, or SMC.
SMC. Right?
Think of it like this. Complexity is basically information integration, how well the bits connect times agency or adaptability, what it can do times temporal persistence, how long it sticks around.
Okay, so those three multiply on top.
Right. And then underneath, in the denominator, you've got resistance, or the resources needed. So more complex means, well-organized, capable, lasting, and reasonably efficient.
Got it. Information, agency, persistence, divided by resistance resources, SMC. Okay, so we're starting from almost nothing and heading, well, let's see, where do we begin? The Big Bang.
Pretty much right after. In those first moments, the universe was incredibly hot, dense, and almost perfectly uniform, like a smooth plasma soup. Complexity, basically zero.
Zero complexity, wow.
Then you get cosmic inflation, this incredibly rapid expansion. And here's the slightly weird part. It smoothed the universe out even more on the grand scale, which
Yeah.
actually made it harder for structures to form right away. That's high resistance.
That-
But it also took tiny, tiny quantum fluctuations, sort of microscopic wobbles, and stretched them out enormously. Those became the initial seeds, the very first bits of information for everything that came later: galaxies, stars, us.
Oh, okay. So it's like stretching a smooth sheet, but embedding these tiny wrinkles that gravity could then grab onto later.
Yeah, precisely. As things cooled down, gravity slowly took over. It started pulling matter together, eventually forming the first stars and galaxies, and even a single star, just fusing elements. That's a massive leap in complexity compared to that initial soup. It's an organized system, processing energy.
And the document mentions a way to measure this, right? Energy rate density. Chesson's idea.
Yes, Eric Chasson's metric. It's basically the energy flow per second per gram of mass. And what's really striking is how it increases. A whole galaxy is relatively low. Our sun, much higher. Earth's biosphere, all life together, higher still.
So you can actually track complexity going up using this energy flow idea.
You can. It gives a quantitative feel for it. And it wasn't just stars, even planets forming with their geology, chemical cycles. That's another jump in information complexity, even before life. Think about layers of rock, weather patterns that stored information, processes happening.
Yeah, and that plot in the document, the semi-log one, it really shows that acceleration over cosmic time. You see the steps. Milky Way, sun, biosphere, each one climbing steeper. So the next big jump must be life itself, abiogenesis.
Oh, absolutely. The origin of life is seen as a huge spike in the SMC. Just think, suddenly you have molecules like RNA or DNA carrying and copying information. That's a massive increase in IA.
Information.
Then you get agency, self-replication, metabolism, that's A, and temporal persistence through heredity passing traits down. That's T.
So I, A, and T all shoot up. But it needs energy, right? That's the catch.
Exactly. It needs a constant flow of energy to keep organizing itself, to fight against entropy, that natural tendency towards disorder. That's the R, the resistance it has to overcome. Earth was in that Goldilocks zone, enough sun energy to fuel complexity, but not so much it just blasted everything apart.
It's interesting that the paper mentions complexity often starting in these sort of protected places like tide pools or deep sea vents, like you need a little shelter.
Yeah, it seems like those marginal, buffered environments allow these delicate, complex structures to get started without facing the harshest conditions immediately. So life gets going, and then does it just climb steadily?
Good question. What's the trend then?
Well, it's generally upwards, but definitely not smooth. It's
Right.
more punctuated. You start with simple cells, prokaryotes, then a huge step. Eukaryotes, cells with internal compartments, organelles like mitochondria, that's modularity right there, specialized parts working together.
Like little machines inside the cell?
Kind of, yeah. Then multicellular life emerges, tissues, organs, again, more information complexity, new kinds of agency, often longer lifespans, but also higher resource needs, higher R, and then you have the big setbacks.
Mass extinctions.
Yeah, those drastically reduce complexity, at least temporarily, within ecosystems.
But they also clear the slate, don't they? Open up opportunities?
They absolutely do. When dominant species disappear, it creates empty niches. Other groups can then radiate, diversify, leading to new forms and often, eventually, a resurgence of complexity, maybe even higher than before. The document talks about punctuated equilibrium, long stretches of slow change, then boom, rapid innovation like the Cambrian explosion, or a massive collapse like the Permian-Triassic extinction, followed by a long recovery and renewal. The system finds ways to maintain that overall energy flow, even if the specific organisms change.
Okay, so life evolves, gets more intricate, and eventually brains appear, the cognitive era. That feels like a game changer for agency.
Oh, it's enormous. Intelligent, goal-directed behavior, that's a quantum leap in A. Animals with brains can sense, learn, adapt, even start changing their environment intentionally. The information processing power, even in simple brains, is incredible. The human brain, billions of neurons, trillions of connections. The coherence is amazing.
The coordination required is just mind-boggling.
And then you add memory, learning across lifetimes. That extends temporal complexity, the T factor, dramatically. We learn from the past, plan for the future.
And humans are sort of the peak of this cognitive complexity so far. The document points to that creative explosion around 50,000 years ago, language, art, complex tools, all appearing relatively quickly.
That was absolutely a threshold moment. It basically launched cultural evolution, which is a whole new substrate for complexity to grow on, and it's way faster than biological evolution.
Right, we don't need to wait millennia to evolve fur. We invent clothes.
Exactly. The SMC of a human society with shared knowledge, tools, cooperation, just dwarfs that of an individual organism. This ability to innovate and adapt culturally allowed us to spread across almost every environment on Earth incredibly quickly.
Which leads us into the last, say, 10,000 years.
Yeah.
The technological and societal era. Things really seem to accelerate here. Agriculture, for starters.
Yeah, the agricultural revolution was huge. Stable food surplus meant permanent settlements, population growth, cities, and entirely new ways of organizing. Hierarchies, governance, specialized roles, infrastructure. A massive jump in the complexity of human networks and their artifacts.
And we see those same patterns, modularity and hierarchy, showing up in our own creations, just like in biology.
We do. Herbert Simon talked about this, how complex systems, natural or man-made, tend to be built this way in nearly decomposable layers. Think of a city's districts or an organization's departments. And just like in nature, we see cycles. Empires rise, become complex, maybe too rigid, and then fall. But often that collapse leads to reorganization and eventually sometimes even higher complexity later on, like Europe after the Roman Empire's fall, eventually leading into the Renaissance and scientific revolution.
And then comes the Industrial Revolution. Fossil fuels unlock this vast new energy source,
leading to another exponential jump. Energy throughput skyrockets, populations boom, global trade networks form, new technological systems emerge everywhere. You get these feedback loops between technology and society, driving faster and faster change.
And that brings us to now, the digital age, the information revolution, the internet as a planetary nervous system.
That's a good way to put it. And look at the SMC components now. Information growth is explosive. Agency is amplified hugely by machines and algorithms. Temporal continuity gets a boost from digital records.
But the resistance, the R, is growing too.
Definitely. The energy demands are enormous. The environmental impact is catching up to us: climate change, resource depletion. And you have social frictions, inequality, adapting to rapid change. Complexity, measured by energy density or just sheer interconnectedness, is at an all-time high in a modern city or the internet itself. But the speed means we're hitting thresholds much faster, facing risks of cascading failures. People talk about a hyper-exponential trend, maybe even heading towards a technological singularity with AI. We're clearly entering a new regime.
Okay, what a journey. So now the document shifts gears a bit, looking for common patterns, resonances, and also key differences, divergences across all these systems. Galaxy, cell, society. Let's start with modularity and hierarchy. You mentioned it pops up everywhere.
It really does. It's striking. Cells have organelles, bodies have organs, ecosystems have niches, computers have modules, companies have departments. It seems like a fundamental design principle for managing complexity. It contains interactions, makes things more manageable.
Simon's point about them evolving more easily.
Exactly. These nearly decomposable systems are just easier to build and stabilize, whether through evolution or design. Specialization becomes possible, and failures can be localized, at least to some extent.
But there's a difference in how they arise, right? Biology versus technology.
Yeah, that's a key divergence. Biological modularity is often messy, the result of evolutionary tinkering. You get redundancies, quirks, things that aren't perfectly optimized biological baggage. Engineered systems can be designed more cleanly, top-down, though arguably that sometimes makes them less resilient, less robust to unexpected problems than evolved systems.
Interesting trade-off. Okay, next. Flows. Energy and information. These seem critical.
Absolutely fundamental. You can think of energy flow as the currency complexity spends to grow and maintain itself. All these systems we're talking about are far from equilibrium structures. They need constant energy throughput just to exist.
Like a star burning fuel or us eating food.
Precisely. Without that flow, the second law of thermodynamics takes over, and order decays into disorder. Entropy increases. Earth's biosphere thrives because it's open to energy from the sun. A closed system just runs down. There's even an idea, still debated, called the maximum entropy production principle, suggesting complex structures might actually form because they're good at dissipating energy gradients, essentially speeding up entropy production overall.
Huh. So complexity might be a side effect of the universe trying to get messier, faster.
Sort of, yeah. It's a fascinating perspective. And information flow is the other side of the coin. It's about processing information to guide and utilize those energy flows effectively. Think brains directing bodies, ecosystems responding to signals, economies allocating resources.
And this leads to larger patterns emerging. Causal emergence.
Right, where the whole system exhibits behaviors you can't predict just by looking at the individual parts. An ecosystem regulating climate, a society establishing norms. These macro-level dynamics have their own logic.
Okay, now the scaling laws section really caught my eye. How biology scales differently than cities.
Yeah, this is super interesting. In biology, you often see sublinear scaling. Think Kleiber's law. Metabolic rate scales with mass to the power of 34. Bigger animals are more energy efficient per cell than smaller ones. It likely relates to the fractal geometry of internal networks, like circulatory systems.
Okay, sublinear for biology.
Yeah.
But cities.
Cities show superlinear scaling for many things. Double a city's population, and you tend to get more than double the economic output or the number of patents, maybe around 115% increase.
Wow.
It seems related to the density of social networks. More people interacting means more opportunities for collaboration, specialization, knowledge spillover. Bigger cities are disproportionately more innovative and productive.
That's a huge difference.
It is. It suggests social complexity operates under different optimization pressures. Maybe biology optimized for energy efficiency and survival, while human society, through its network structure, has inadvertently optimized for information exchange and growth. It's also why cities seem so resilient, almost like superorganisms that constantly innovate, while companies, scaling more like organisms, can often die.
Fascinating divergence. And the last comparison was evolution versus design.
Right. Biological complexity arises through Darwinian evolution, undirected trial and error over vast timescales. Technological and social complexity involves some foresight, some planning, even if our rationality is bounded.
And that affects the outcome, the type of complexity.
It seems to. Evolution often builds in redundancy, making systems robust, but perhaps not maximally efficient. Human design often aims for optimal performance, but that can sometimes lead to brittleness, making systems fragile to unexpected shocks. Failures can cascade quickly in engineered systems.
Whereas natural systems might degrade more gracefully.
Often, yes, though we are learning. Think about the internet. Its distributed, decentralized structure was partly inspired by biological networks, making it more resilient than a centralized system would be. And you also see convergent evolution.
Where different systems find the same solution independently.
Exactly. Like the eye evolving multiple times in different lineages or similar algorithms being invented separately. It suggests there are underlying principles, maybe optimal solutions or attractors in the landscape of possibility that different complex systems tend to find.
So summarizing this section, lots of shared architectural principles like modular networks and flow dependency, but key differences in scaling and how innovation happens due to different constraints and mechanisms. Very cool. Now let's get into thresholds, tipping points, and cycles. This feels crucial for understanding change.
Absolutely. Complex systems don't always change gradually. They often undergo abrupt shifts when they cross critical thresholds like water boiling, a phase transition.
And these tipping points are where the SMC factors really shift the balance.
Often, yes. A change in information flow, a leap in agency, a breakdown in persistence, or a sudden increase or decrease in resistance can push a system across a boundary into a whole new state of organization.
And sometimes these lead to incredible novelty, right? Like life itself or language.
Exactly. Those are thresholds where complexity didn't just increase, it qualitatively transformed. Often, a seemingly small trigger can have massive effects if the system is primed for change criticality. Think of a tiny spark setting off a forest fire, or maybe specific brain wiring enabling recursive.
The system builds up potential and then snaps into a new configuration.
Sort of, yeah. Near these critical points, information can flow more easily across scales, allowing new patterns to emerge. We see it in ecosystems flipping states or societies undergoing revolutions. It's not just more of the same, it's something fundamentally new emerging, like consciousness. In SMC terms, I times A times T finds a new way to overcome R, creating a new stable state.
But tipping points aren't always positive, are they? They can lead to collapse, too.
Unfortunately, yes. If a system loses resilience, its ability to absorb shocks, it can be tipped into a less complex, often undesirable state. That ball and cup analogy works well here. A resilient system is like a ball in a deep, wide cup, hard to knock out. A vulnerable system is in a shallow cup, easily tipped over.
Like a lake turning into an algae swamp.
Exactly. Or critical climate tipping points like irreversible ice melt. And societies can collapse too. Joseph Tainter argued that societies can become overly complex, getting diminishing returns on their investments in complexity, making them fragile, top-heavy. Then a shock hits drought, invasion, disease, and the whole structure becomes unsustainable. Resistance overwhelms the system's ability to maintain its complexity. IXAXT.
But even collapse isn't always the final word, right? There's this idea of cycles.
Yes, the concept of adaptive cycles often associated with C.S. Halling. There's a growth phase, R phase, then conservation where things become efficient but rigid, K phase, then a release or collapse phase, A omega, followed by reorganization, A alpha, which allows for new growth.
Like the forest fire example, destruction, release of nutrients, then new growth.
Precisely. Or historically, the fall of the Western Roman Empire led to fragmentation and chaos, but eventually that release allowed for new forms of social organization, new technologies, and ultimately the conditions for the Renaissance and beyond a higher level of complexity eventually emerged. Resilience, the ability to reorganize after disturbance, is key to long-term persistence.
So for us today, that means fostering flexibility, adaptability.
Absolutely. Even Earth's biosphere went through huge collapses, the mass extinctions, but life reorganized, and the overall complexity trend resumed upwards.
That brings us back to the present global situation. The interconnectedness is so high. It feels like any collapse could be global and catastrophic.
That's a valid concern. The potential scope of collapse is unprecedented. But complexity science also suggests, first, that targeted interventions, those small corrective nudges, might help steer us towards safer pathways, think smart policy, sustainable tech adoption. And second, even in worst-case scenarios, some parts of the system, some knowledge, some capacity, would likely survive and could reboot a new cycle.
So understanding these dynamics might help us avoid the worst. Stay within safe limits.
That's the hope. It's about managing the SMC, boosting information, agency, and persistence, while actively working to reduce the resistance factors like environmental degradation and social instability to keep our global system within a resilient, stable basin.
Okay, let's look at the present and near future now. Global civilization, AI, this coupled system. The document analyzes this using agency, coherence, and resistance. Let's start with agency. Who's acting?
Well, it's clearly not just humans anymore. AI agents are increasingly acting in the world, making trades, driving cars, diagnosing diseases, sometimes making decisions faster than human institutions can react. The A in SMC is definitely rising as machines amplify our capabilities.
Which offers huge potential.
For solving big problems, yes.
Yeah.
But also risks if AI goals aren't aligned with ours or if powerful AI is misused. So a big focus now is on AI safety and ethics, trying to ensure alignment.
And agency is spreading out, too.
Yeah, technology is diffusing power. Small groups, even individuals, can have outsized impacts, for good or ill. So governing this complex system with all these different human and non-human agents is a massive challenge.
Okay, so agency is increasing and fragmenting. What about coherence? Are we all pulling together or pulling apart?
That's the million-dollar question, isn't it? Achieving coherence is tough in a world with so many competing interests. But there are forces pushing for integration, too. Global communication tech creates this potential global brain. We see hints of it in global scientific collaborations, maybe even attempts at global climate agreements. There's talk of a metasystem transition, where humans plus machines become a more integrated, higher-level entity.
But lots of things pull against that coherence, too.
Oh, absolutely. Geopolitical tensions, polarization, filter bubbles. These things fragment us, risk creating a split brain scenario where different parts of the global system work against each other. High coherence would mean effective global governance, shared norms, interoperable systems. It would reduce resistance. Low coherence means friction, conflict, inefficiency, potentially destabilizing the whole complex system.
And AI could push it either way.
Exactly. AI could help bridge divides, improve understanding, or it could be used to deepen divisions, spread misinformation, automate conflict. The next few years seem critical in determining which way that balance tips.
And finally, resistance and resilience. The headwinds and our ability to cope.
Right. The REM and SMC. Major resistance for global civilization comes from hitting planetary boundaries, climate change, biodiversity loss, resource limits. Basically, the entropy cost of our complexity growth is feeding back on us.
We're creating our own resistance.
In a way, yes. And there's social resistance, too. People struggling with the pace of change, job displacement from AI, ethical objections to new tech. But resistance isn't always bad. It can force adaptation, spur innovation, build resilience.
Like climate change driving renewable energy development.
Exactly. Or privacy concerns pushing for better data ethics. Building resilience means creating buffers, diversity, feedback loops, things like decentralized grids, diverse crop genetics, international safety agreements. The argument is we need to consciously design for resilience, maybe using insights from complexity science itself to build more adaptive institutions.
So putting it all together, we have this emerging human AI system that could either synchronize and become sustainably complex or fragment and potentially collapse under its own weight and external pressures.
That's the crossroads we seem to be at. The goal, thinking with the SMC, is to boost the numerator, IAT, intelligence, adaptation, long-term thinking, while managing the denominator, our entropy, conflict, waste. There's potential for a leap to a new level of coherent complexity, maybe that global brain, but also a real risk of stagnation or breakdown. It really highlights the need for conscious stewardship, using systems thinking to manage these powerful new technologies and global risks.
Which leads perfectly into the final section, future scenarios.
Yeah.
The document sketches out several possibilities based on different constraints: energy, ethics, computation. Touch on the main ones. The continued acceleration scenario sounds like Star Trek.
Sort of, yeah. It assumes breakthroughs in clean, abundant energy, maybe fusion works or space-based solar. Energy constraints ease up. Technology, especially AGI, continues advancing exponentially, but crucially, we manage to integrate it safely and ethically. Global governance keeps pace.
The singularity, basically.
Something like that. Skyrocketing complexity, maybe a transition to a digital biological civilization. Information I and agency A go off the charts. Temporal persistence T might increase through longevity tech or space expansion. If resistance R is managed big if, you could see sustained exponential growth for a long time. Think Kardashev type I or 2, a truly integrated global or even interplanetary system. Cosmic limits exist eventually, but this is the optimistic, expansive vision.
Okay, then the opposite, limits to growth.
Here, the physical constraints bite hard. We fail on energy, climate damage gets severe, scarcity dominates. Innovation might slow as focus shifts to just coping, adapting. Complexity could plateau or even collapse if crises hit hard. Think resource wars, population decline, forced simplification. SMC numerator shrinks, R dominates.
Is there a middle ground in that scenario?
Yes, a managed, steady-state variant. We consciously accept limits, cap growth, focus on stability and equity within those limits. Still high-tech, maybe, but lower energy throughput. Deliberately managing R, accepting capped I and A, like a mature ecosystem. Stable, coherent, but not exponentially growing.
Then there's ethical control development. We choose to slow down.
Exactly. Society decides, maybe through global agreements, to put the brakes on potentially risky tech like AGI or unregulated biotech, prioritizing safety, equity, quality of life over raw growth. Complexity increases, but more slowly, linearly. Information might grow, but be carefully managed. Agency deliberately constrained, time persistence potentially increased through long-term planning. Resistance kept moderate.
Safer, but maybe slower progress.
That's the trade-off. Less risk of catastrophic failure, but maybe slower to solve big problems, potentially missed opportunities. It assumes very high global cooperation to maintain those controls. Could lead to a long-lived, stable civilization gradually improving.
How about runaway chaotic growth? Tech races ahead, but governance lags.
That sounds risky. Tech and economic forces push complexity way up, but the controls, ethics, regulations, institutions can't keep up. Think AI arms races, unregulated experiments. You get very fast, but brittle growth. High I and A, but very low coherence, high friction, high R from systemic stress. It feels like a recipe for a major tipping point into collapse. The more complex and tightly coupled the system, the more devastating the failure, a sharp peak, then a crash.
And finally, what if computation itself hits a wall? Innovation slowdown.
This assumes Moore's law really ends and we don't find a successor. AI progress stalls, digital tech slows down, a major engine of recent acceleration sputters out. Society might settle into a kind of technological plateau, complexity growth slows or levels off.
Good or bad?
Could be both. Might give us breathing room to sort out governance and sustainability, might reduce AI risks, but could also make it harder to innovate our way out of problems like climate change. Maybe we just muddle through with moderate complexity SMC-wise, agency capped, information growth slows, resistance might remain high if big problems aren't solved, could be stable or could lead to gradual decline, a status quo plateau.
And looking really far ahead cosmically.
Well, even if complexity expands beyond Earth, the universe itself has a trajectory towards heat death, maximum entropy. Eventually, R will dominate. The resources dilute, energy gradients fade, I, A, and T must ultimately decline. Life might find clever ways to persist for a long time, but on cosmic timescales, complexity likely rises, peaks, and then falls. We happen to live in the rising phase. It's a reminder that perpetual exponential growth is impossible. The window for complexity might be finite and precious.
So no single predetermined future. It hinges on how we manage energy, tech, ethics, environment. Our choices matter immensely.
Absolutely. The potential for incredible futures exists, but so does the potential for stagnation or collapse. The key seems to be adaptability, resilience, feedback, diversity, learning from nature's playbook, using AI to enhance our wisdom, not just our power, and constantly asking, complexity for what purpose? Is it serving life, flourishing, meaning?
We've covered an incredible span then, from the Big Bang simplicity to this intricate, hyper-connected world we're in now, facing these profound choices about AI and our global future.
And that shared metric of complexity, the SMC, gives us a lens, imperfect perhaps, but useful, to see common threads of the role of energy, information, agency, persistence, fighting against resistance across all these scales.
And we, humanity, find ourselves as, well, kind of the lead actors in this current chapter, holding this immense legacy of past complexity and shaping what comes next.
It's a profound position, almost like the universe, through us and our technology, is becoming self-aware, starting to consciously manage its own complexity. Our success hinges on understanding those deep principles: balance, flow, feedback, ethics.
It's hopeful, though, that the resonances we discuss, the shared patterns, mean we can learn from biology, from history, about building resilient, adaptable systems. And we do have unique tools: foresight, planning, global communication.
We do. We need to remember complexity is more than just more stuff. It's about that rich interplay of information, agency, stability over time, all woven together despite the constant challenge of resistance.
Viewing ourselves, our civilization, AI, all as part of this larger unfolding story, part of the Earth system.
Exactly. And we're clearly at an inflection point. Multiple paths diverge from here. Will we navigate towards a flourishing, sustainable complexity, or become another data point in the universe's history of complex systems that rose and fell?
The answer, as you said, depends critically on decisions being made right now. Those patterns of creation, crisis, renewal, understanding them, feels like the best wisdom we can have for the future.
Indeed. The spiral can continue upwards, hopefully in an adaptive, sustainable way.
And remember that we, listening to this, are institutions. We're all agents in this system. We all have a role.
Let's hope for the necessary humility and foresight to guide things well, keeping those SMC components in a healthy balance.
Because the story of complexity is definitely not over. And maybe the best, most coherent, most life-supporting chapters are still ahead, if we choose wisely. Thanks for this incredible deep dive today.